So, good morning, everyone. So I will tell you a little bit about drying of colloidal systems, and it will be essentially an experimental point of view. So there will be some movies and cartoons and so forth, not so many equations. And one thing I want to give you to tell you is that basically it's important to combine different techniques to get more sense out of your experiments. So drying, it's easy to, well, everyone has a feeling of what is drying. There's no way to explain it. I mean, everyone knows. And you can experience it if you look at the cement, mud, of clays, when you have this transition from something which is liquid-like or viscoelastic to something which becomes solid. You also have drying in different fields which are related to some industrial applications. So when you in the coating industries or when you paint, you have you have your dyes, and then you dry it to make a uniform feel, hopefully. Okay, attends. Ouais. It's on. Ah, it was off. It doesn't work. Ah, c'est bon. Okay. Yes. It's also important in food industry. No, that it works. Okay. Thank you. It's also important in food industries. For instance, all the dried mix that you have, it's made of droplets of mix that you dry in very rapidly to form these powders. And it was also very popular with the COVID in the COVID period, because in fact, if you have aerosol droplets with virus inside, there was all this question whether what's going on when the droplet shrinks because you have water evaporation. Does the virus survive or not? And there was a lot of work and discussion about also these aerosol particles. But more generally, and this is a picture taken from this review, drying could be important in a very broad range of length scales. You see here from the nanometer scale to the 10 to the 6 meter scales. And just I want to point a few examples which I like this one. For instance, if you look at, there are people looking at the drying of blood, and they look at the pattern that you have, and from that you can get information, whether two kind of information, I guess, forensic science to know where the blood has been ejected, what was the impact of the blood drop on the surface, and also apparently if you have several diseases, for some diseases you can have different pattern of your blood, so it could be useful also from some diagnostic. For instance, you have also here blisters in the cosmetics in film, and you see that when it dries, you have these little spots. And of course, this is something you don't want. You don't want when you put some cream on you that you have these little blisters. I guess it's not very nice to feel this. You also have these nice patterns like in permafrost, and you have the cracks in Mona Lisa, and also some larger scale geological motion. So why I decided to give this lecture was first because as I just showed you, drying is an ubiquitous processes that you see. Yet we all feel, and we have a direct feeling of what's going on. It's also ubiquitous in applications, so it could have some understanding this could be useful. It's a control out of equilibrium processes, meaning that once you fix the evaporation condition, like you fix the relative humidity, you will have water evaporating in a controlled way, and it's a way to have this out of equilibrium process in a way which is different from what you could have when you apply a mechanical force or stress. It's another way to drive your system out of equilibrium. And this is something I will try to show you, that it touches on different fields. And to understand drying, you need to understand different other fields, and that's what I want to show you. First, a quiz. So it's soft matter. So the school is about soft matter. So who knows who introduced the term soft matter? You disappoint me, Simon. No, actually, it's not de Gene. It's this woman, Madeleine Vessier, in the 70s. She was a close collaborator of de Gene. She was an experimentalist. She's still alive. And she introduced this term as a joke, like in the 70s. And you see this picture was during the ceremony of the Nobel Prize, all those nice men and just one woman. And she's a great scientist and great person, actually. So I was trying to look at how to define soft matter, and I look on the web, soft matter, and I found this cartoon, which I like, from IOP. I like it, but I don't understand it well. So maybe everyone will have his own interpretation. Okay, I can see like a polymer here. I see that it's soft and the material is soft and deformed, but then I have this. I don't know what it is. Then I say, okay, they put a small electric field, and what that is that molecules, colloids, and you have this shape. Well, I mean, everyone could have his own interpretation, but basically what the message was that it is what exists between liquid and solid, and of course all the viscoelastic material that we heard about. And if we look at drying, would be that we go from this liquid to this solid. So more traditionally, we have all these building blocks for soft matter: micelle, protein, polymer, colloid, surfactant, and so forth. And I will focus here on colloid. And I will focus on very simple colloid, not this fancy shape and active colloid with patchy interaction and so forth, just simple, non-deformable spherical colloids. Okay. So I will tell you a little bit about the drying of a drop of colloidal suspension, of a drop of colloidal gel, and there will be some interludes where I will explain you a little bit of things which allow us to understand what's going on when we dry this colloidal material. So let's look at a movie. And so this is just the control experiment. Let's say a drop of water, okay? I don't know why it doesn't play itself. So it's under control humidity, and then it shrinks. So you see a lot of stick slips, and then it disappears once it has evaporated fully. So in the literature, you will see that this is they speak about the d squared law, which means that in fact the dynamics of reduction of the volume varies like the radius scale as the square root of time, or the radius square scale linearly with time. And this is derived from a simple, let's say, simple Fick's law, where you consider the diffusion of water from in the air. Okay, so you have a diffusion equation here with the mass of water vapor that over the surface R of your droplets, and then you have the gradient of vapor concentration along a radius here. Okay, then if you integrate this, you got this equation where these two parameters. These two are the concentration at the surface. Vapor concentration at the surface are infinite, and basically this control the relative humidity of the system. And it will control the speed at which you will evaporate your drop of water or your colloidal materials. And just combining this with mass conservation, you end up with this evolution of the radius of your drop with time, okay? And this is the d squared law, okay? And of course, you have a lot of different details that might change is law when you have a gradient, when you have force, when you have something which is complicated, but in some case you can find this law. Okay, this is our, let's say, our control experiment, just a drop of water. Now I will put some colloids in my drop. So the experiment, I like this experiment, which was done in the group of Dave Waits 20 years ago. And they put a drop on with colloids on a hot plate, very hot plate. And this is called Leidenfrost conditions. Does anyone know what is Leidenfrost? Yes. So it's so this is exactly what you said. You have a very hot surface. It should be much hotter than the boiling, and then you have this vapor layer, and then that insulate the drop from the surface. Therefore, you don't have any. The temperature is much lower, and you don't have any friction. It's a way to have something that levitates on a cushion of vapor. It was first mentioned by this person, Johann Gottlob Leidenfrost, who is actually a medical doctor. And you have it.
Previous video is a vertical section, or the first video we just watched horizontal.
Yeah, you look at transmission. So you have it when you have a pan and you put water on it. You see that they move rapidly. It's also, I don't know if some of you, maybe it's not very popular anymore. This Jules Verne is a novel. Michel Strogoff is a novel from Jules Verne, the French writer. And basically there is this Michel Strogoff, and they try to burn his eyes by putting a very hot sword on his eyes. But he didn't get blind because of this Leidenfrost effect, which makes that there was a vapor layer that protects his eye from burning. So it's I mean, it could be useful to know about this Leidenfrost effect. So they have this drop levitating onto this host plate, and what they observe is that the drop shrinks, and then you have this instability, buckling instability, the shape instability of the drop, okay? And all this paper was about how to understand and rationalize why we have this instability. And one important parameter to understand in general this experiment, but usually the experiment when you have a confined, and essentially it's a drop of a sample with colloids or with stuff inside, but we'll speak about colloid that shrinks, is this which is called Peclet number, which compares two time, the evaporation time, characteristic evaporation time. And basically what people do when they want to compute this is to take the characteristic evaporation time that would have in the same condition a water drop, okay, that as we have seen just before. And they compare this time to a mixing time, which is the time needed for the colloids to mix just by Brownian diffusion, okay? So this evaporation time depends on the experimental condition, the relative humidity, the temperature.
Yeah. Neglects completely microconvective instabilities that can speed up the mixing. Yeah. In this description, you only consider diffusion.
Yeah, exactly. Yeah. I mean, I think it's a way to give you an idea whether you are at 0.1 or 10 to the 3. Then you see, if you're in between, you're in problem. So it's just diffusion. So it depends on the radius square and the diffusion coefficient to get the time, okay? And basically, when this Peclet is small, which means that the particles have time to, when the drop shrinks, the particles have time to mix, okay? And convection will help to have this mixing stuff. Well, you expect to have a homogeneous drying, particles everywhere all the time, okay? When this Peclet number is very large, particles don't have time to mix. So when you shrink your drop, you shrink the colloids which are close to the interface. They don't have time to go back to the center, so then they get trapped at the interface, and you form what is called a shell, a crust, a skin, depends on the community, depends on people. But you have a portion of your material which is concentrated with more colloids at the interface, okay? And if we put numbers just in the Leidenfrost condition, where, so you see you have very hot plate, but the evaporation time, it's like 100 seconds. So it's not very fast because you have this vapor that insulates the drop. And we have a Peclet about 5,000, so very high. So we expect to have this shell. Okay. So what was assumed in this paper of Dave Waits and Sapis that you have a step function with a volume fraction of colloid in the center, which is what we have put inside at the beginning, the initial volume fraction, and you have a step function, and here you have a shell with a certain volume fraction, phi shell, okay? And what they assume is that, okay, I have this, and then I have evaporation. So the evaporation is due to the flow of water through this porous shell, very porous dense shell, okay? And you can model this. This is exactly the Darcy flow, where you have flow of a material through a porous materials. And then you can define a Darcy pressure. We depend on the viscosity of what is flowing through, so water, on the thickness of your porous material, so the thickness of the shell here, on permeability, I will come back to that, and on the flow, which is the derivative of the radius, so how this radius decrease with time. And the permeability is often modeled as with this Karman-Kozny relation, which depends. I don't know if it has, I didn't check whether it has been, if it's empirical or if there is some, I think it's empirical, but I didn't check properly. But basically, it's something that depends on the size. A is the radius of your colloids, and on the volume fraction of colloids. So basically, it gives you how much, the quantity of pore where you have liquid flowing through. So what they say that you have this Darcy pressure, and this Darcy pressure gives rise to a Darcy force between the colloids, which is simply by dimensional analysis, depends on the Darcy pressure times the square of the particles. Okay, this is the force acting on the colloids. And because of this force acting on the colloids, you have maybe I show you before. I didn't tell you. Do I have it here? Yeah. So usually our colloids are, in this experiment, they are charged colloids. So this is a DLVO potential. I think we have seen this with Mehdi. Didn't tell that it was DLVO, but DLVO is more from an experimental point of view, where you have something attractive, which is this van der Waals attraction, and you have some charge. Usually you have charge around your particles. And you have some electrostatic repulsion, this double layer repulsion here. And the combination of the two is what is called this DLVO, for Derjagin-Landau-Verbeek potential, where you have a minimum here, where usually your particles are sitting, so they are well stabilized and well separated one from another. And you have a barrier which can be very high, which prevent the particles to come close together, and therefore you don't go to this second minimum and you don't have attraction. But what was proposed in this paper is that because of this force, you can go over this energetical barrier and get particles coming close together and become solid. Okay, and once you have this solid shell, if you have solid shell and down you have some evaporation, it has to shrink. But then you have this shell where you cannot readapt the surface. I mean, it's a solid stuff. You cannot have solid stuff that remains solid and well spherical when you shrink it. You need to have some instability to accommodate the the variation of volume with the same surface. Okay, so that was the idea of this model. So, and what they assume, because what they assume is that the shell has a constant volume fraction, 0.58. And with this shell, with mass conservation, if you have the shell volume fraction, you assume that this one is constant, you can evaluate the thickness. And then you can make computation about the Darcy stress and see how it varies when you change the particles and so forth. Okay, that was the model. Okay, porous solid shell that cannot, with a constant volume fraction of particles that cannot accommodate any change of surface, so buckling. Then there was a lot of people looking at the drying of colloidal drops on surfaces, essentially. And because it's important also for patterning, for getting different things, so they look at all kind of shape you can have, or what the resulting of what you have. And these people, Bazou and collaborator, make like a summary of what can be observed with simple colloids, different volume fraction, and different substrates. Okay, from glass, which is essentially hydrophilic, so you have your drop in the initial drop, which has this shape, till something where you increase the hydrophobicity of the drop till something super hydrophobic where you have this shape, okay? And they look at what's going on, whether you have buckling, meaning whether when it dries, whether you have some shape instability or not, depending on this parameter and on the volume fraction. Okay, in this experiment, it's usually at room temperature, so so the drying is slow. And if you compute, if you evaluate the Peclet, it's about 50, so much lower, 2 orders of magnitude lower than what we have before. Still 50, you could say, but it's quite big. And basically what they saw and what they show is that you have a crucial role of the interaction with the surface to evaluate what's going on with time, and you have very often shape instability. And they put this in a phase diagram. Okay, initial for different initial volume fraction, and as a function of the contact angle. So very hydrophilic this way, very hydrophobic this the shape of your drop here. And basically, you can identify 2 zones. One where you don't have any buckling. If you are very hydrophilic, you don't have any buckling. It goes in a smooth way. And if you are very hydrophobic, you have some buckling. You have always buckling. Okay. Just one interlude about this hydrophilic surface, and this is where you have, maybe you have heard about this coffee ring effect, of your experience it when you drop a drop of coffee on a surface, and then you see that you have a stain, of course, but the stain is not uniform. Usually you have, this is the original pictures in this paper with this coffee, and you have more, it's darker here, so you have more particles at the interface. And the simple way to understand this is that this is a case where you have so you have an hydrophilic drop, and then basically with this kind of hydrophilic drop, you have a non-uniform evaporation flux. So it evaporates more here than at the top. And if you want to keep, because the drop is what is called pinned, the drop stays there, there's no retraction of the drop, because you have a higher evaporation here, you need to have a flux of particles going from the apex of the drop going to the edge. Okay, and this is what they show here. This is an overlay of different images of your particles that goes toward the edges here. And at the end, eventually, you get more accumulation of particles here, and this is your coffee ring effect. I don't want to speak about that. I will go to the opposite case, where it's very hydrophobic, and where you have always buckling. And what we want to understand is what drives this buckling. Is it always what has been proposed by the group of Dave Waits 20 years ago or not? Yes?
So the ring effect that you showed, does it disappear if the drop is in between two plates?
Yeah, maybe because you don't have this. Well, I don't know, but for sure you don't have the same evaporation field. So it might. Maybe you don't see it. If you confine, you don't have this effect of having a fixed contact angle. So I guess you don't have it. Yeah. So in all these experiments, and especially here, these people and others always have the same qualitative interpretation that I have a shell with colloids at random close packing, 0.64, and therefore it's solid, and then you have buckling. Okay, so it's really the common argument that most papers put forward. Okay, so this is what has been proposed for this Leidenfrost experiment. Basically, so you have, just repeat it. So you have this, you have a strong force between the particles. So your shell becomes, you have some attraction. So your shell becomes solid with pores. And because it's solid, it cannot accommodate any more surface variation, and therefore you have buckling. And in the paper of SAPI, they assume constant at 0.58, and then later on, I didn't make all the paper, but most people now assume Fischl at random close packing 0.64. And they all assume initial volume fraction at the end is in the center is what you put inside at the beginning. But I would say there's not a lot of experiments on probing this shell, checking whether we have a shell, what is the volume fraction, what is the thickness, blah, 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 blah. So there are a few.
The idea is that the particle would stick, right?
Stick and go to the minimum potential, so get solid.
More aggregation.
Yes.
Yeah,
more gel, but yeah, it depends what you call a gel when you are at the high volume fraction.
Yeah, but why would they go at such high volume fraction? I guess that you push them. I mean, we'll have a lot of voids.
Yeah, it could be this way, but that's not what they assume. They assume very high contact. Not much. I will show you a few experiments now that of this, but because before that, just let me know that how people have looked. So we have seen that some people looked with this to look at one single drop, let's say, without as much as possible interaction with the surface, as less as possible interaction with the surface. So you have this Leidenfrost that we have seen. I've shown you that these Bazu people look at a super hydrophobic surface. So you have a particle that touches not with a minimal interaction the surface. You have also experiment when you have some levitation with acoustic or aerodynamics field. So you have a drop that levitates between two materials. You have also experiments which are similar to what you have in industry when you do spread drying that you generate drops, and then you have a very high temperature so that it shrinks very rapidly. So they can make this also in lab experiments. And you have also a drop hanging on a filament, okay, like this one. And I wanted to show you this paper, you see, 57. And he got already this nice or night. I don't know if it's nice or if it's a nightmare, but all the zoology you can have when you have a drop hanging with colloids inside. And he speaks about the crust, the shell, and he has different stuff about the crust, which is rigid and porous, rigid and less porous, pliable, rigid and less porous, plastic. So anyway, the fact it was already recognized in 57 that the fact that a crust, a shell, a skin, whatever you want to call it, is very important. And it reminds me that the previous talk of Alessandra, that in all, like with this Blair element, that in old literature you can have a lot of information and things that sometimes we feel that we discover, but it was done like several decades ago. So this kind of zoology that has been also shown more recently, where they have same kind of cartoon, and they assume, they observe that you have different shape of the drops at the end, and they consider that for some camp the shell is porous and rigid, skin they call it here, or it's smooth and flexible, and that the ultimate state of your drop would be different. Okay, but let's say, okay, now the next step is, okay, let's try to measure what's going on. Does this shell exist? What is its structure, the volume fraction, the thickness, and blah, blah, blah. So there are not a lot of experiments. You have a few experiments in 2D, because it's easier. So you confine your drop between two plates, okay, and you look from above here, and then it evaporates from the side. And in this paper of Ludovic Pochard and collaborators, François Boulogne, they had some colloidal fluorescent particles, and they look from above at the interface, and you have the drop here and the air. And if you look at the profile, the fluorescence intensity, you have an excess of intensity at the interface. Okay, this is plotted here. This is a the profile along this line. Okay, and from that, there is a proof that you have an excess of particles, which could be defined as your shell. Okay, and they can measure the thickness of the shell. And this is experiment with time, and they have the shell, and then you have this, you see also in 2D, you have this speckling instability with time, okay? So there was no information about the volume fraction of the shell, for example, but it shows that we have a shell. There was also people doing more sophisticated using more sophisticated techniques. Again, a drop confined between two plates, and they'll use some interferometry setup to evaluate the concentration of the drop, the concentration of the colloidal concentration inside. Okay, and they end up with this kind of 2D map. So this is the volume this is a scale for the volume fraction, and this is time. Okay, so with time you see that the interface. The interface between this shape, because you have a reduction of your drop, the radius of your drop, and you see that you have a higher concentration at the periphery here with time, and slightly here, if you make a cut like this, it's slightly more yellowish in this part than here, which is shown here. These are cuts. Horizontal cuts, where you see that you have an increase of the volume fraction at the periphery, but it's very different from the profile. We see that it's flat and very abrupt profile where you have the shell. So it looks like a smooth evolution, and you are always lower than this random close packing. But still, you see that you have a slight accumulation of particles toward the interface. But it's in 2D. You could say, okay, in 2D, maybe in 3D is different. So there are a few experiments in 3D, even less. For instance, you can hang your drop on a capillary and then do X-rays. So I don't know what Luca said about, well, you speak about dynamic light scattering, but in static light scattering, like you can have in X-ray, you can have an idea of the structure of your samples. Okay, we'll come back to this later. Here, it's not important. You measure the structure as a function of the different wave vector, okay, with time. Okay, you got this signal, which are complicated to analyze. What they What they compute is what is called a port invariant. It's not very important, and I don't know exactly why they compute this, but they compute this. This is the integral of the scattered intensity as a given wave vector times q squared, the wave vector, and you integrate 0 to infinity, means from in the q range you can measure. Okay, so you integrate, you multiply by q squared this, and you get the integral. And you have this kind of data, okay, experimental data. For instance, if I look at this one, this experimental data at different positions, because you look at different positions like this, you move different, you have a motor and you look at different positions along your drop, okay? So you see that your drop shrinks because you have a signal out over a smaller range, and you have this shape, and sometimes you have this shape here, which is different. And to get some information of what's going on, they compute. Okay, they compute assuming a shell and doing the same experiment, looking at different positions. What would be the Porot invariant if I don't have a shell? I have this shape, which looks like this, and if I have a shape, I have this shape, which looks more like this. Okay. And based on that, you can say, okay, in some condition I can have a shell or not, but it's model dependent. It's difficult to have a lot of information about what is the volume fraction because it depends on a lot of factors. But still, there is the proof with a structural parameter that you in some condition you can have a shell, an accumulation of particles as the interface. And the last experiment I wanted to show is with confocal, where you have a drop and they use two dyes, one for the nanoparticles and one for the solvent, and they look close to the surface. They have a super hydrophobic surface, and they look close to the surface, okay, and they look at the profile, okay, and you have this kind of profile, very noisy because it's very difficult experiment. You have 3D and just look very close to the interface. And they do a lot of image analysis, and the evidence that you have a shell, I didn't put, but here you have a shell, and they measure, they can compute also some thickness of this measurement, but they can just do it at the beginning of the drying process. They find that the shell thickness increases with time, which goes in the correct direction with what we have heard about, that it grows as the drop shrinks. But there was no measurement buckling, so there was no possibility to see what's going on, what is driving this buckling, if it's related to some properties of the shell or not. And there was no measurement of the volume fraction, just saying I have an accumulation of stuff here, of particles, okay? And just one slide about modeling. There are also people that model. This is Sobak. This is a recent paper. They have a drop of colloid. They put some condition to calculate all the heat flows and the vapor flow, and so they can look at how the drop shrinks. They put some they put some information with the volume fraction of the drop, that the diffusion coefficient changes when you concentrate, it moves less. So they can compute a lot of things. Still, they assume phi shell equal 0.64. And I don't understand why this is a parameter that they cannot model, but they assume that you have these shells. And they look at different Peclet numbers. You see that we have large Peclet number. You have a shell, you have really a step profile, okay? With this assumption here, and you have a shell that that thickens with time, and it becomes well, no shell if you are very close to Peclet 1, so things have time to mix. And intermediate Peclet, you have a shell. Ultimately, you have a shell, but everything is smoother. But still, you have this assumption 0.64. It doesn't help us to see to give. This is one important property of the shell that was not inferred but was assumed. Okay, so this is again the same slide, just saying that okay, of very few measurements about the shell thickness, the volume fraction of colloids in the shell, and the dynamics of the shell. Okay. And this weird transition between assuming 0.58 and now assuming 0.64. So what I want to tell you, I want to show you what we can learn from a technique that was introduced by Luca Cipoletti yesterday about photon correlation imaging, which in very shortly give you some information about the dynamics with a space and time resolution. Okay. And with this, I will show you 3D experiments on 3D, so 3D drop, where we will image the drying process and check whether we have a shell and get some information about this shell, okay? So just movie, it works. Okay, so now this is the same kind of imaging. I look in transmission about one drop, but I have particles inside, 30% small particles of diameter 20 nanometers. Okay, so it shrinks a little bit, and I have a second movie. Later on, what you see is that you have this instability, and then it breaks, okay? So you have this instability. And basically, all the experiment I'm going to show you just to understand why we have this instability. So first thing we did, very simple experiment, nothing to do with this PCI complicated experiment, just to say, okay, one assumption is that I have a solid shell, and this is what drives the instability. So here what I'm doing, I say, okay, I let my drop dry, and at some point I take it out and put it in water and check whether if I have something aggregated, aggregated shell, I will have it. If everything dissolved, means that it's not aggregated. And to check whether my particles are aggregated or not, what I do is standard dynamic light scattering that you have explained. Yes. Which give me the size of my particles, okay? So this is the correlation function of the function of t. And in yellow, this is what you have when you batch. You take your batch particles. So you have this correlation function give you some size. So if you take at certain time, in all this zone, green zone, you take the drop here, and you put it back in water, and you check what you have. And all along this process, even here, when you have this instability that we see here, you have this data, the black data, which are on the below, underneath the yellow curve. So you don't have any aggregation. It's fully dissolved. Okay. So there's no evidence that you have something solid. I mean, everything is fully dissolved. Even if you have dynamic light scattering is very sensitive. If you have a little bit of higher particle, it will dominate your system. So your response. So you don't have, everything is totally unaggregated here. By contrast, when you have at the last stage of this drying, when you have cracks, fracture, and even here breaking into two pieces, here you have aggregation. Okay, aggregation because you have larger relaxation time, which means larger particles. And even to get this, we need to sonicate to break the part to get the small pieces, but still you have aggregation. Okay, so there is something that you have. This shape instability doesn't need particles to be solid, to be aggregated in a solid. Then we can do a PCI in a very on the drop. Basically, this is what Luca has shown yesterday, and we can have a look. We shine a laser through a diameter of the drop, which is a drop which is drying when it's drying, and we look at the dynamics at different positions, so in the center of the drop and at the periphery. Okay, and we do this. And as something I told you in the beginning, we change the speed of evaporation by changing the parameter Cs minus C infinite that I showed you before. And basically, you change the relative humidity with different chemical component, and therefore you can reach different Peclet number. And the range is between 60 or 400. So it's large compared to 1. So first thing we can look at the speckles, okay, this time, and this is along a diameter. So maybe you have a trained eye now that you can see something or not. You see fluctuation, but do you see something more than just fluctuation? Yes. It's shrinking, yeah, because we are trying. But if you look, here it fluctuates a lot, here much less, right? So to emphasize this difference rate of fluctuation, what you can do is you can average these images over a certain time, okay? If you average something that fluctuates very fast, we get something gray. If you average over a period where it's comparable, slower than the fluctuation, you will see some speckle. You will see this speckle. And this is what we show here. So if you average over 4 seconds, at the beginning you have something which is homogeneously gray. And then with time, when it shrinks, and this is, you see the shrinking because the edge just translate to the center of the drop, you see that you have a transition from something, you have a quite sharp, rather sharp transition between a part where you have some speckle images and a part when it's homogeneously gray. Okay? And this is what we call the shell, and I will show you why, but this is what we call, there is something where you have here a slow dynamics and there a faster dynamics, okay? And from just this kind of average images, you can evaluate the thickness, okay? This is the thickness of this part. And here it's normalized by the radius, but you see that it increases with time, okay? For all Peclet number, okay? More quantitatively, what we can do is compute this correlation index or correlation factor. I don't know how Luca called it yesterday, but based on this two-time correlation function, and look at the dynamics in different portion of your, in different domains in your drop, in the center, in the periphery, and in between. Okay, and you have this two-time correlation function that depends on the time, the real time, since the beginning of the evaporation, and to the delay between the two images you compare. Okay, and with that you calculate correlation function. Okay, instantaneous correlation function. So at a given time, this is what you observe. In the center you have a fast decay, and if you go to the periphery you have a much slower decay. Okay, and from this correlation function, you can extract a relaxation time, because it's easier than to plot one, instead of plotting a curve, plotting one number is easier. And you have a characteristic relaxation time. And this is, at a given time, you have this relaxation time is a certain value, and then you have a quite abrupt increase by almost 2 orders of magnitude of this relaxation time at a certain position, okay? And you can do this for different time. So you start from something homogeneous, let's say homogeneous dynamics at short time, and then as the drop shrinks, evaporates, you see that you have this huge increase of the relaxation time that emerges and becomes occurs at a larger and a smaller and smaller distance from the center. So you get something, let's say this, the proportion of this slow dynamics increases with time, okay?
Question about the boundary between that slow crust and the inner part, because it looks almost as if it's a step jump, but there must be particles that are just sort of coming in and.
Yeah, this is the problem. This is the problem. We have a nice, very short space resolution. So no, we don't. We cannot have a better resolution in space. It's probably not sharp. I mean, there's no way it should be very sharp. You should have then whether the profile is very smooth, but for sure it's quite sharp actually. But in if a few micron, you have a lot of, I mean, compared to the size of particle, it's super large. So it's probably
So is this like a binning type process where you just have fixed boundaries and then you look at everything within that boundary and then the next and then the next as it's drawn at the top?
Yeah, more or less, yeah. You average your signal. You need to have enough speckle to get the correlation function, decent correlation function. You average the signal.
Yeah.
Yes?
Volume fraction in the middle of the droplet. The relaxation time jumps by 2 orders of magnitude during this experiment.
Yeah, so what happens?
So what would be the initial volume fraction and the final one in the middle, not in the crust?
So yeah, good observation. We come to that later, but the fact that the relaxation time increases, in fact, the mark, and I will just show you that the volume fraction in the center increases. Okay, it's not that we have always the same dynamics.
Value of the volume?
Initially, the volume fraction is 30%. Okay, and then it's increasing. And I'm going to show you.
Okay.
Well, I'm going to show you, yeah, how we understand this. Now we have correlation. Well, we have correlation function and relaxation time, which is not very intuitive parameters. But what I'm going to show you is that there is a direct mapping between the relaxation time that we measure and the volume fraction. Okay, and this is shown here. This is a paper from Luca, which was done measured in the same condition, but in capillaries with a fixed and controlled volume fraction. So, and you look at the microscopic relaxation time, which is the one that we compute and I showed you before. Okay, at low volume fraction, you are in the dilute regime, and the diffusion coefficient is independent on the concentration of particles. They are isolated particles. Okay, but then if you increase concentration, then they start to feel each other, and you have some steric hindrance, and therefore the relaxation, they move less, so the relaxation time increases, and it increases and increases, and you have a huge. See, you have 8 orders of magnitude. So you have a huge increase of the relaxation time. And at some point, your system is more or less stuck. And this is what you call the glass transition. Okay? And here it's about 0.49 or 0.4. And basically what is show you that in all these zones, not at in the dilute regime, you're not sensitive to the volume fraction. But if you are in this regime, you are extremely sensitive to the volume fraction, which means that you can have a mapping between the microscopic relaxation time that you measure and the volume fraction of your sample. Okay, and because of this mapping, you can. This is your remark. Here we look at the core. We have this huge increase of the relaxation time, which in fact is due to an increase of the volume fraction in the core that we can that is plotted here. So you have an increase with different Peclet number with time, and you have an increase. This is an experimental observation. You increase the volume fraction of even the core of your particles. Not that it's a constant, and we think get stuck at the boundaries. Then we do something quite bold, because it's probably not reflect the reality, that we assume that we have a step function, okay? That we have the volume fraction in the core, and we have a shell with a step function with a thickness h. But this time the thickness is that we measure the thickness. This is what I showed you before when we average the speckle images. So we average the thickness here. We measure the volume fraction in the core, and therefore, for mass conservation, we can measure the volume fraction in the shell, assuming that the shell has a fixed volume fraction, okay? And it's really sharp. And this is what we obtain. Volume fraction of the shell as a function of time. Well, this is normalized by the evaporation time. And basically, all the data collapse more or less, very noisy, but still, whatever the Peclet number, they all increase this time, okay? So we don't have a fixed volume fraction in the shell. It gets denser and denser with time. And it's very far from this 0.64, okay? It's between 0.40 and 0.50, okay? But it increases with time. And the other thing is that this phi glass is what I showed you before, the time where everything is stuck that we see, and we are always above. So which means that if the sample was at rest, everything will be stuck. There's no dynamics of the shell, yes? I go back. If you look at this here, you have the real radius of your particles, this diameter 25 nanometers, but then you have this red stuff, which is in fact the fact that they are soft because they are charged, and you have an effective radius, which takes into account the fact that you have this repulsive potential. Okay? No, the blue one. Okay, and this is why your volume fraction for the glass transition is at this value of 0.4. If you have hard spheres, just if you have particles where you don't have this soft I won't call it shell, but the soft region where you have this repulsion, the glass transition is about 0.58. Okay. Okay. So the shell is a glass. That's why we could say with this value compared based on what we observe in a sample at rest in tubes, we are in a glassy shell. So now we did this experiment. We could be like a toy experiment, but we learned a lot about this. So we do this experiment. We have our drop in air. It evaporates. We know that we have something where we have a shell. Okay, we have a more concentrated part here. And then we put it back in oil, okay, where we stop evaporation, okay? So what's going on? It was a simple question we have, okay? Any idea what's going on? Any intuition? Yes? Exactly. Because we don't have any interaction. We have seen in the experiment that it dissolves. Okay. So that's what we did. Hopefully Matteo, who did the experiment, doesn't have to wait an infinite time because after 10,000 seconds it was over. So what you see is that you start with the shell, and then with time, okay, this profile becomes smoother, and at the end you have something flat. Something flat means that you don't have any difference in the diffusivity of your particles in the center and the periphery. So we have dissolution of the shell, which is expected because we have seen it before, and we know that it's a glass and it's not a gel. There's no strong force between the particles. Okay, so it dissolves. What we see also, which is consistent, is that if we look here at the center, with time, the relaxation time increases. I'm super slow. The relaxation time increases, therefore, because we have this mapping, the volume fraction increases in the center, okay? Which is okay because we have this dissolution of particles from the periphery to the center. So if they dissolve, it becomes more concentrated in the center, okay? Do you see something weird? Exactly, that's the weird stuff because if I dissolve, it means that at the periphery I have less particles. If what I told you is true, less particles means faster dynamics because I have, okay, while I see the dynamics which become slower again. And here comes rheology, we'll be happy. That the fact that what's going on, we are not at equilibrium, we have a drop that shrinks. And basically, we can define a deformation rate, okay, at the periphery, which is simply 1 over r dr over dt, which is a deformation rate in second minus 1 unit. That has a drop, and that drives the deformation of the shell, okay. And how we can look that? So we say, okay, this is the important parameter. So we plot our data, the relaxation time at the edge as a function of this parameter. Okay. What we observe, different Peclet number. At the beginning of the evaporation, we have vertical lines. What does it mean? It means that my epsilon dot, the evaporation rate, is constant. Okay, it's constant and it's faster when I have a large Peclet number, when I have something drier, less relative humidity lower, so it shrinks faster, and everything is controlled by the relative humidity, and it shrinks faster when it's drier. Okay, and it's the same whatever my Peclet number. But then, so it's a regime where everything is governed by the evaporation, okay, the relative humidity. Then sometimes you end up in another regime after a time where you have your point, you see here, which is on this line, which has a slope, don't write it, of -1. Okay, this is another regime. When you have this, and this regime, when you have this, you have a relaxation time which is inversely proportional to the rate at which you force your system, and it has been observed in a lot of solid-like materials here, colloids in 2D, in 3D, polymers, and so forth. And it's really a regime where you are solid-like regime, okay? Where basically you remember we have a glass, the shell is a glass, and we are here limited. What drives the relaxation is the relaxation of the shell, okay? And this is this regime. And what you see is that but then you say, okay, these points are above. When I am at low Peclet, so basically I have to compare the time at which I force the system to shrink and the time my shell can reorganize, knowing that my shell is a glass with a high volume fraction. So if my evaporation is very fast, like in the yellow, for instance, I try to shrink faster than what I can do with my relaxation. Therefore, I end up in this regime, okay? And then after this regime, I will have instability. If I evaporate slower, it's not that my shell is different, it's that the time scale at which I drive my system is larger, so my shell has time to reorganize, and therefore I continue to have a regime dominated by evaporation. Okay? And when I have this regime dominated by evaporation, till the end, I have a constant shrinking of my drop, no instability. If I drive the system faster than what the glassy shell can do, I cannot cope with this fast evaporation, and therefore I have this instability, okay? I should go super fast. So just in a minute, basically we have this fancy title, but it's just to say that if I have something which is quite large in Peclet number, okay, this time, I have two instability instead of two regime, and I have this regime where it's driven by evaporation. Then I have the glassy regime where everything is governed by competition between the glassy dynamics and the evaporation dynamics. And then if I continue to break, I will break and aggregate, and I have this aggregation, okay? If I go much slower, I don't have this driven dynamics because I go sufficiently slow so that even the glass can cope with this rearrangement. And I just have a transition from evaporation to aggregation. Okay. So far, we have just looked at simple particle charge, okay, repulsive, no, quite simple, well, simple that goes to the glass transition. If we look in this diagram, concentration of salt 5, we were here, no salt. I didn't tell you that I have salt. And therefore, I always have my repulsive potential, and I was here, and I have my glass transition somewhere. Very often in experiment, you have salt, okay? You have a little bit of salt which screen a little bit the interaction, but then when you shrink, your concentration of salt increases and increases, and therefore you end up in these lines, okay, where you will have a large amount of salt, which can induce, because you have that's what Mehdi showed yesterday. The barrier that prevents aggregation becomes smaller and smaller, and at the end you don't have barrier, and you end up with having aggregation, or in the best case, a gel. Okay. But it's complicated. If you do experiment where you have at the same time shrinking shell, changing the potential, it's a nightmare. So what we do in our experiment, we say, okay, let's start from a position where we have a gel already, and then it's not important anymore whether I have a little bit of change of concentration. So what I do is that I screen so I have this shell that we talked before, because I have this repulsive interaction, and then I put salt or something else. I put salt so that I remove this potential, and therefore there's no repulsive barrier between the particles, and they attach through van der Waals. Okay, and if you do this, they attach this time, and what you end up with is fractal gels. Okay, that we have heard yesterday with the talk of Mehdi. Okay, and this is what we are going now to see: how a colloidal gel shrink. Okay, so this is now we have seen this, and now we are here. Okay, very far from all this problem we could have with this change of concentration of salt. We have a gel. If we have a gel, if you ever go to, if you have a chance to go to the museum, one of the few museums, was of several museums in Ville, you can see this painting of Egon Schiller. Okay, if you zoom here, what you see is this cracks. Okay, this pattern. I didn't ask him, but I'm not sure it's on purpose that on this small side he put this pattern, but I think it's really cracks, okay, that you could have. And cracks, you have them in a lot of colloidal gel when they dry. So you have a lot in the Mona Lisa, you have it in mud, in model colloidal film, and in fact you have the same pattern, and I think Zorana showed some of this mud patterns. You have the same kind of pattern that you could have in other type of out of equilibrium processes. So it's interesting, and it gets nice. You can get nice pictures, but it's very complicated. Why is it complicated? Let's say, what is the basic? Why do you have these cracks? So you have a substrate, and you have your gel on top of the substrate. And you have to assume that you have strong adhesion between your substrate and the gel, okay? So when it evaporates, so you have water coming out. Since you have a strong adhesion between this and this, you have some tensile force. I mean, the sample wants to shrink, but then it is attached. So you have some tensile force stress here. And this force, well, you can imagine even like in a very approximative way. It's touched to the surface and it's tried to pull it apart, you get cracks, okay? And in my opinion, it's not easy, I'm not an expert, to understand what governs, what controls the crack formation. So there are several parameters, and I want just to list these parameters. First, you have what is that you may have heard about. This is that you have in linear fracture mechanics, which is called the Griffiths law, Griffiths theory, which it's simple in its way. It said that a crack will propagate if the reduction. So if you have tension, you will have you store the elastic energy. And what he said is that if the crack will propagate if the release of elastic energy is larger than the energy you need to create two interfaces. Okay, basically, if you gain energy by creating a crack. Okay, so maybe I don't go. So it's so you can make with scaling arguments. You can evaluate this. So I did this here in this slide. The Young modulus is Y. It was K in previous talk. But then you can rapidly compute what is the deformation. So it's a scaling argument. I don't put the prefactor, which I don't know how to put them, and then it's complicated. But you have a deformation, which is basically the tensile stress that you have divided by the Young modulus. This is a Hooke's law that we have seen before. And the stored elastic energy will be the Young modulus times the deformation square, okay, this. And then you say, okay, how much do I release energy when I get a crack of length L and extension L? So basically you said, okay, I have this, I look at this volume. So it's this volume divided, or L, which scale as L square. This is a crack length here, divided by the thickness, because I am in a thin film. So my volume is L square H. So I release this energy, okay? E elastic times L square H, so sigma square over Y L square H. And what is the energetic cost that I have to pay is the energetic cost to create two interfaces, to create an interface between air and my sample, okay? So it's a surface energy times the volume, the surface of my crack, which is L times H, okay? So if I make the balance, the total energy is this, the released elastic energy and the surface energy that I have to create. And what Griffiths said is that, okay, the crack will propagate if this term is negative. So if L, if I take this, so if the length of my crack is larger than this, which depends on the surface tension, the Young modulus, and the tensile stress to the square, okay? Or equivalently, you could say, okay, I have pre-existing micro cracks, and they will propagate if my tensile stress is larger than the square root of gamma y over L. Okay, this is a Griffiths criterion, which apply only if you have a perfectly elastic material which breaks in a brittle fashion. So you have this, but then you have something else that you have to take into account, that you have air invasion. If you open a crack in a material, you have air coming in. And it's not easy to have air coming in, because then if you have when you have a colloidal system, it means that your particles are not wetted anymore. So you have a capillary bridge. You have air here, and here you have a capillary bridge. And if you have a capillary bridge, you have a pressure drop, which is huge because this is small. The pressure drop is gamma over R, okay? Where R is very small because it's the pore between your materials, and because you have small particles, it's super large. And if you have 100 nanometer particles, you say that you evaluate that the radius that you have here between the pore would be like a fifth of this, 20 nanometers, and then you have 10 megapascal. So it tells you that another way to see whether I have crack or not is that whether it's easier to deform my material than to create this very strong capillary bridge, very, very curved capillary bridges. Okay, so it gives us another parameter that has to be taken into account when we try to model or to understand what's going on when I have a colloidal gel attached on the surface. Then you can have delamination. Delamination, I'll go fast here. There are some people showing experiment, but basically it tells you that you don't have a very strong adhesion, but then at some point it can buckle, and then it can partially buckle like this, and then you have parts when you have adhesion, parts where you don't have adhesion, and it changes the pattern that you would have. All of this means that it, no, sorry, I wanted to show you this. Oh, yes. So this delamination tells you that how the material adheres to the surface is very important, whether it's super strong or not. And in this nice experiment, they showed two examples, okay, of colloidal film, colloidal gel. So this is a fully adhesive substrate. You see that you have all these cracks and this pattern. And they put a non-adhesive substrate, non-adhesive at all, and what you see, your gel shrinks, but in a very smooth manner, no patterns at all, okay? And if you're in between, you are in trouble. And basically, you are in trouble when you have all this going on at the same time. I could have Griffiths, the comparison between the stored release elastic energy and the surface energy is important. The curvature of the interface is important. I have maybe my interaction, which is not super strong. So it's super complicated. So the strategy we have, and I will show you in a minute, is to say, okay, when you have interfaces, it's complicated, okay? And it's complicated from this experiment I show you, but also, for instance, when you have a gel that collapses, you have how it interacts with the wall is important. That changes the time at which it collapses and the way it collapses. And even in shear experiment, depending on whether your plate are smooth or rough, you will have different whatever. It's not important what quantity we have here, but the rheological quantity will depend on the way your gel adhere to the surface. Okay, and it's complicated to control very precisely. So our strategy was to say, okay, we want to remove all the interface, easier. So we said, okay, let's look at what we have when we put a bead of gel under stress, okay? Here we don't have any interfaces anymore, so it's easier. And we say, okay, maybe it's just a way to look really at the intrinsic property of the gel because there's no interference with the surface that may bias or impact the response, okay? So we do it in a very simple way. You put a drop with colloids, and then we add an enzymatic reaction to produce salt, and then to induce aggregation of the particles into gel. And then we have our gel, we take this bead, they are typically a few millimeters, like the drop actually, a few millimeters of diameter, and we look at what's going on when they dry. Maybe I come back to this later. We can have a look at the structure. We can get information about the structure, but I come back later if I have time. Let's look at the movie. It shrinks. So you have seen that it shrinks. I play it again. I don't know why it cannot play. No, it was continuing actually. Nothing happens. So I do it again. It shrinks. You have a change of color, and then stay there for more than 10 hours. Okay, nothing happened anymore. It stays there and it doesn't move. Okay, it doesn't change. So we can plot the volume. So we see that we have a decrease of volume. Okay, as we would have for the colloidal suspension or even the drop, it shrinks, and then it stops. And when it stops, we have this change of color that I guess you have seen. It's not very clear here, but in the movie it's seen, it changed the color, and because you have air invasion, I will show you better later on how we know that we are something else happened at some point, and then doesn't move anymore. Okay? At least macroscopically. And here from what we learn about this, actually you have air invasion when it becomes easier energetically to create this capillary bridge than to shrink more your elastic gel. Okay, you can see better if you look at a speckle movie. Okay, with time, in principle, what do you see? Good, not much. You see fluctuation. Well, it's very dark, sorry. But then you have to trust me, we show you data that there was no differences as we have seen before between the edge and the part. And then it becomes white, a lot of white, and then you cannot see anything anymore with this technique. And this is where you have this air invasion. You have a strong, the index of refraction, you have interfaces and blah, blah, blah. And then you cannot do anymore this light scattering, but this is the second regime, okay? If you look at the dynamics, here I just show you the relaxation time, relaxation time at different position. Basically, it's flat. Well, you say it fluctuates a lot, but if you remember before with the suspension, we have 2 orders of magnitude differences here, small variation. So basically, it's homogeneous. At this length scale, it's homogeneous. There's no differences. There's no shell or cross, whatever. It shrinks homogeneously. Since we learned before that this epsilon dot is a very important parameter, we can plot this average relaxation time as a function of this epsilon dot parameter. And you have all your data, different initial volume fraction, different type of gels, okay? So what do you see? You see, well, you recover this -1 that we have seen before, and this dashed line is what is called an affine. It's what you expect if you have an affine compression, meaning that you have something that shrinks this way, like would do a perfect elastic body, okay? And basically, you have something slightly lower with this prediction of affine motion, but it seems independent of the drying rate and the initial value fraction. It seems quite boring, actually, compared to the shell where we have all this instability. So we say, okay, let's look at the mechanics. So to look at the mechanics, we take a rheometer, we take the bead, and we compress it in the linear regime. So we plot here we plot the normal force as a function of the indentation depth, okay? And you have this Hertz contact model that gives you access to the Young modulus, okay? So we take our gel and we dry it and take it at different drying time and look at what is the Young modulus. So we have this curve, okay? So this is a pristine gel. So the gel before drying, okay? Different volume fraction, okay? From 2 to 10, okay? The higher the volume fraction, the higher the elastic modulus. It's more or less what Mehdi showed, that you have this power law here. It's 3 point something that you have that you observe in many different conditions. And then the small points are what's going on during the drying, okay? So if I take this orange one, it dries, it becomes, I increase the volume fraction if I dry by definition, and then it increases, but it follows the same line. It's the same for this one, this yellow, follows the same line. And it seems boring. Basically, whatever you do, you have the same, you dry, you change the volume fraction, but it just depends on the volume fraction. It does not depend on the fact that you dry or not. If the points were all the same size, they look all superimposed. So nothing. Quite boring. So we did, we have to find something, what's going on and what is the structure and so forth. So we went to synchrotron, and I need to stop. So basically we look at the bead of gel when it dries, and we follow with time the structure. At least for once it changes. I don't have time, I think, to detail this, but basically we see changes when it dries. And what is important, at least from here and to connect with what we have heard yesterday, is to look at samples with same volume fraction, okay? Some which were pristine, not dry, this one, and some which were dried, till they get the same volume fraction of 10%, okay? So we have seen that all these samples have the same modulus, same Young modulus. Still here we see differences. Well, you can argue whether it's big or small differences, but you see differences at this length scale. And what we can identify is this length xi. It's not exactly the same as Mehdi, but it's what poor experimentalists can do, is the size over which the sample looks homogeneous. So it's a size over which the signal is flat, and it's more or less the cluster size, okay? This is the cluster size that you have for a pristine gel. What we see is that this size, 1/xc decreases, so xi increases when we dry the system. So the system with the same volume fraction, but which has dry to reduce the volume fraction, is more heterogeneous. Okay, you need to look at a larger length scale to have something homogeneous. So it's more homogeneous. So then that's more or less my last slide. Is we can plot this like this. I take this Young modulus, the y that I plotted before, as a function of this this value psi, this length scale that we can measure by SACS, by X-ray scattering. What we see that, for instance, if I take a line here, I can have samples with different, with the same Young modulus, okay, 10 to the 7, but with different structures. And this is where we are, and this is nice time to stop. Just to conclude, that there might be some hidden length scale, or well, basically we need to connect this structure with the elasticity that we can measure. It's not easy to rationalize because we find different structures, same modulus, and what I wanted also to say is that this drying is it's drying, but it's also a nice experiment to make isotropic compression of a material without any boundary, without being bothered by boundaries. With that, I conclude. I like these two sentences. So I was in another summer school a few weeks ago, and there was these two sentences. Rheology without morphology is theology. And then Richard Stein, and then Ronald Larson replied, morphology without rheology is zoology. So basically, everything is important. It's nice to combine different techniques to get information, and dynamics also is important, that, as we have seen for this glassy dynamics, because glass has the same structure as a liquid. And so here in this talk, I show you different things. When we look at the drying colloidal system, we need to have to take into account the rheology, the morphology of the whole object, the mechanics, hydrodynamics, fluid mechanics, colloidal stability, capillary interfaces, and other things. And with that, I stop and thank my collaborators, and you, of course.